little wings, and they don't move efficiently, and you waste a lot of energy, and you don't get all the thrust that you wanted to get. So if you ever study in physics, it's just relative velocity and vectors that you study, I think, in 256. Is that right? So commercial jets, they achieve 15 to 60% pressure increase, and they're about 90-95% efficient. Military jets, they can achieve over 100%, which is double the pressure that is at the inlet. But they do it by sacrificing some efficiency. They think it's more important to go fast than to save gas. And that's true if you're trying to be killed. Pardon me? Try not to be killed, right. Okay, so there were problems when we started trying to go too fast. And I'm almost done. Everything was nice. The wing was holding the boundary layer just fine. And then we started going too fast. So here's what happens. Air is moving across the surface of this wing, and the pressure is dropping. The pressure is dropping because, let's see here, how do I explain it? There's this equation called the Bernoulli equation. There's this Italian guy, Bernoulli, and he said that velocity and pressure are related to each other. So basically, over the surface of the wing, if the velocity increases, the pressure falls. And if the pressure falls, it makes the air speed up. So we've got really fast air moving across the surface of this wing, which means we have very low pressure on the surface of the wing. And where am I going with this? Oh, so inversely, the low pressure that's on the surface of the wing is creating very fast air. So as the air moves very fast along this curvature, the place where it begins to curve the most is where the velocity of the air is the fastest. And so even though your plane is not going the speed of sound, air over the top of the wing is. Even though it's going at a particular velocity here, it speeds up as it gets across the top of that wing. And we get what we call a shock wave. And so here's how shock waves work. Air is a bunch of particles hanging out in a group. And if you're moving slowly, they can all see you coming. And they say, hey, somebody's coming. And they all start moving away. Right? And the wing goes right by. But when the wing is moving at supersonic speeds, the speed of sound, they're all standing around. They look over, and there's this wing all around. They freak out. Ah! They go into shock, literally. And there is a huge pressure difference that happens when you go through this shock. So the speed of the air right here is supersonic. It's above the speed of sound. And right here at the boundary where the shock is occurring, there is a huge chemical change. There's pressure, there's high temperature, and what happens is the velocity slows down. So you're fast here and slow here, which means that you've got, let's see, slow means high pressure. And then here you've got low pressure. So if you have high pressure on this side and low pressure on this side, what happens is the velocity begins to reverse itself. Instead of flowing from front to back, if the shock is strong enough, the flow goes the other way. And everything separates, the pressure is gone, and your wing falls out of the sky. And this happened to a lot of people during the early 40s, late 40s. They were trying to fly the speed of sound with regular wings, and they would go on, the whole airplane would hit a shock wave. The nose of the plane, the wings of the plane, and essentially it would hit that, they call it Mach 1, the speed of sound, and the drag would be so big, it essentially like running into a giant marshmallow. It would just almost stop it, and it would just literally fall out of the sky. So I wanted to show you a little video, if I could, of an airplane photographed in a video, actually, breaking the speed of sound. It's kind of cool. The transition across that shock is basically squeezing the air so hard and so fast, it vaporizes the air in a matter of seconds, and you see this giant hot vapor cloud around the outside of the plane. I hope I can show it to you. Oh. So he's about. You can see the cone. It's called the Mach cone, and he's right here. He's squishing the air, and the air is about to just bust out. Because you can see the shock starting to form at the very edge, the discoloration right there. That's the air is starting to be gaseous. I don't know if it's going to work. Oh, well, maybe it doesn't work. So what happens? How do you get planes to fly at supersonic speeds? Oh, here we go. Oh, I thought that was really fun.
If you restart it, it'll be loaded all the way.
Oh, you think? Okay, let's... So he was flying low on purpose so everybody could get a big kick out of the breaking the sound barrier. Most of the time that's against the law. Why? Because it breaks people's windows and wakes up their babies. Okay, so I'll try to make this quick. How do you fly really fast? And here's what we found. The curvature of the wing when you are supersonic hurts us. There's a lot of drag. There's all kinds of shocks forming on this thing. You can't avoid shock waves. You have to have them. But there are equations that tell you how shock waves react to something that they are hitting. So turns out that one way to fly really fast is, instead of having a big, thick wing, is to make a very thin wing. Very, very thin wing. And instead of having camber or curvature, we gave it kind of a diamond shape. We gave it a diamond shape. And so at low velocities, this thing doesn't create much lift at all. At low velocities, this thing hardly flies. So what we do is we attach a very powerful rocket to the jet, or to the airplane. And when you are taking off, you basically launch yourself into the air. You take a rocket, it makes you go really, really fast. And you angle, I didn't draw it very well, but if this is horizontal, then there's this angle called the angle of attack. And so you pitch the angle of the wing up a little bit so that it moves forward. And instead of getting the nice pressure above through a cambered wing, what we do is we sacrifice all of that, and we just let the bottom of the wing push the airplane up, because we're moving fast enough to get that reaction from the air. So the air is pushing on the bottom of the wing, and that gets us to take off. And once we're up in the air, we use the engine, the rocket engine, to blast us off to a super high speed, fast enough so that we are now supersonic. And so what happens when you're supersonic is immediately you get a shock wave on the front of that wing. And it goes both ways. It goes on the top and the bottom. And because we're at an angle, let me show it more. Because we're at an angle, the more perpendicular the angle is, the stronger the shock is. So because the angle is pitched, because the wing has some angle of attack, the shock wave on the top is not as strong as the shock wave on the bottom. So the pressure on top is less than the pressure on the bottom. Remember that after the shock wave, the pressure is huge. Shock waves make huge pressure increases in the air. So now you've got low pressure over high pressure because of the supersonic shock. And then here, at the diamond shape, we have what we call an expansion wave. And the air is now, it notices there's more space. Immediately there's more space. So the air expands into that essentially higher volume. You've gone from a little bit of volume, if you can imagine a little box right here. And then when you get to this side, now you have more space. So it expands, the gas expands, and as a result of that, you get, again, low pressure on this side of the expansion shock. So we built low pressure by making shocks appear, even though they're adverse at low speeds.